In last lecture video, we derived a stiffness matrix for three-noded triangular element for solving 2D elasticity problem, and we assumed the u vector to be linear within the element, and we wrote the displacement as n matrix multiplied by the nodal displacement matrix, and we use the three shape functions which are linear in x and y. So u is actually a linear function of x and y. If we differentiate it with respect to x, y to obtain the strain, so strain equal to del s u, then we get del s n u e vector, and we call this del s n equal to b. So this epsilon vector, which is the strain vector, becomes equal to B matrix multiplied by UE, and we saw that this B matrix is a constant matrix since n is linear with respect to x and y, and that means n is of the form of alpha plus beta x plus gamma y. So differentiating that with respect to x or y, we get a constant number, either beta or gamma. So B is naturally a constant matrix, and that we derived in the last lecture video. That really means that a strain itself is a constant. Because UE is constant, this is the nodal displacements, this B is constant, so multiplication of these two matrices is also a constant, and that really means a strain is constant. And hence this three-noded element is also known as constant strain triangle, or CST element. So this three-noded element for 2D elasticity problem is known as constant strain triangle. That really means we can also get the shape function such that we can get a strain as linear. So next thing we are going to learn is about linear strain triangle, or LST element, that we are going to do now. So linear strain triangle, as the name suggests, the strain has to be linear, that is B has to be linear, and since B is linear, which is a derivative of n, then n has to be quadratic. So that really means shape functions. Shape functions are quadratic. Okay. So in order to derive that, we will have to assume the number of nodes to be 6. So we have nodes like this one. So let's call it 1, 2, 3 as we did earlier, and then we call it this one 4, this 5 and 6. So there are 6 nodes now. We will assume that point 4 is exactly in the middle of points 2 and 3, and similarly the other two nodes 5 and 6. Also note that we are assuming 1, 2 is joined by a straight line and 6 is in the middle of that line, and similarly 5 is in the middle of line joining 1, 3, and point node 4 is in the middle of line joining 2 and 3. Now the first thing would be to convert using the triangular coordinate system, and we will convert that into isoparametric element. So we will apply the same coordinate system, the triangular coordinate system that we have applied earlier while studying the 2D heat transfer problem. So here we apply such a way that this becomes xi1, this is xi2, whereas the original coordinate system is in x and y. Here we have xi1, xi2 coordinate system, and this is 0, 0. This point is point number 3, node 3. Then along xi1 we have node 1 whose coordinates are 1, 0, and along the xi2 coordinate system we have node number 2 whose coordinates are 0, 1 in xi1, xi2 coordinate system. The other points we can find out, the point here, the 4 will be here, which is actually midway between point 2 and 3. So coordinates will be 0 and half. Similarly, this one is the node number 5, whose coordinates will be half, 0, and the node opposite, node 3, on line joining 1, 2 will be node number 6, and coordinates will be equal to half and half, because this is in midway of line joining nodes 1 and 2. So this we did using some transformation, and the transformation was, as you can recall, we said xi1 equal to, rather x equal to x1 xy1 plus x2 xy2 plus x3 xy3. Okay, where okay, we write also y equal to x y1 xy1 plus y2 xy2 plus y3 xy3, where xy3 is equal to 1 minus xy1 minus xy2. So let's check whether it's valid. So what it's saying is, if x if xy equal to 1, we know that if xy equal to 1, we know that all others will be 0. So xy2 will be 0, xy3 will be 0. So you can see here, if xy equal to 1, xy1 equal to 1, then xy2 is 0, and since xy3 equal to 1 minus xy1 minus xy2, so automatically 1 minus 1 minus 0, xy3 is also 0. So we get x equal to x1 when xy1 equal to 1. Similarly, we get x equal to x2 when xy2 equal to 1, because xy1 is 0, xy3 is also 0. And we get x equal to x1 x equal to x3 when xy3 equal to 1, that is when xy1 and xy2 both are 0. So you can actually put those values here and you will see that this is valid in terms of x, and similar logic can apply to u to y, and you can see that if this is valid for x, this will also valid for y. Okay, let's rewrite it. So we can write x equal to x1 xy1 plus x2 xy2 plus x3 1 minus xy1 minus xy2, and similarly y equal to y1 xy1 plus y2 xy2 plus y3 1 minus xy1 minus xy2. So we get x equal to x1 x3 plus x1 minus x3 xy1 plus x2 minus x3 xy2. Similarly, we get y equal to y3 plus y1 minus y3 xy1 plus y2 minus y3 xy2. Okay, so this is how x, y and xy1 xy2 are related. So this is just the relationship between the two coordinate system, nothing more than that. Now remember, our original element is 6-noded element like this one, which has been transformed to the isoparametric element like this one. So we have to write the displacement u xy as a function of displacement. So as a function of the nodal displacement, so the nodal displacement, if this is 1, 2, 3, then you have 4, 5, 6. So we will have, for example, for node number 1, you have u1 or rather ux1 and you have uy1 here. So this is the nodal displacement of the first node. Similarly, for node number 2, we will have ux2 and uy2 and so on. So let's that vector, all of them, this one is actually the, we can write basically in terms of ux, that's the x component of the displacement. So ux is given by summation ni. So I equal to 1 to 6 because there are 6 nodes, and we have ni multiplied by uxi. Similarly, the y component of the displacement vector is given by summation I, let's call this j. So j equal to 1 over 1 to 6 nj u y j. Okay. Now we have to find out what the shape functions are. Now we have to find out the shape function. So we have node 1 here, node 2 here, node 3 and 4 here, 5 and 6. So in order to find out n1, so here, so this is a xi1 and xi2. Okay, and ni will be a function of xi1 and xi2. Okay, this is isoparametric element, and we have seen that in isoparametric elements we define shape functions in terms of the shape function in which it has been transformed to. So xi1 xi2 is where it has been transformed to from the xy coordinate system. So this we have to find out. Okay, and how to do it? So as we learned earlier, in order to find out n1, what we need is we have to find out the lines which will not include this node. So which lines? So one line will be this vertical line and the other will be like this one. What is the equation of this line? Equation of this line, this is the vertical line passing through the origin, and hence this line is nothing but xi1 equal to 0. So we can write n1 is equal to, there will be some constant here, but we just write here xi1. Xi1 equal to 0 is the first equation which will be passing through nodes 2, 4 and 3. So 2, 4, 3 are covered with xi1. Second line will be a vertical line passing through this one, passing through 5 and 6, where we have, remember the coordinate of 5 is half 0 and coordinates of node 6 is half and half. What you see here, the equation of the line that passes through 5 and 6 both will be xi1 equal to half, because both of them have xi1 equal to half. So xi1 equal to half, so let's write it xi1 minus half. So there are two lines. If you make this equal to 0, there will be one line passing through 5, 6. If you make xi1 equal to 0, there will be a line passing through 3, 4, 5, 3, 4 and 2. So hence this is complete now. Now we know that n1 has to be 1 at node 1, where xi1 is 1 and xi2 is 0. So if you put xi1 equal to 1 here 1, we get half. So that really means we have to divide by half. That means we have to multiply it by 2. So now we can put, if xi1 equal to, if xi1 equal to 0, n1 will be 0. If xi1 equal to half, n1 will be 0. If xi1 equal to 1, then this becomes 1, this becomes half. So half times 2 is 1. So n1 is complete, which is a function of xi1. It turns out to be a function of xi1 only. But n1, this is how the n1 we have come up with. Now next will be n2. So how to find out n2? We will do similar analysis. So n2, if you look at, it will have two equations. So one will be xi1, xi2 equal to 0, and other will be xi2 equal to half. So this is same as this one only, however this will be in terms of xi2 only. So you have xi2 and then xi2 minus half is n2. What about n3? So n3, now n3, in order to find out n3, we have to see which two lines will not include 3. So what we see is one line is this that passes through 1, 6, 2, and other is passes through 5 and 4. So we have to find out what is the equation of this line passing through 1, 6, 2, and we know that this is xi3 equal to 0. That really means this is equation 1 minus xi1 minus xi2 equal to 0. Hence this will be 1 minus xi 1 minus xi1. Let's write it, this is nothing but xi3 equal to 0. So we write xi3, rather we write xi3 equal to 0. Let's write it again. So we will write here some constant and then xi3, and as we have written here, we can actually write the same way. So and we will check it. Okay, so xi3 minus half. Since if we are calling it xi3, the third coordinate system, as we have seen earlier, so we call this way parallel to this will be, so this way xi1 is going, xi2 will be going up parallel to 1, 3, and xi3 will go this side parallel to this line. So this one is xi3 equal to 0, and at node 3 xi3 will be equal to 1. So that really means this is in a way symmetric with respect to xi1, xi2, xi3. So if for n1 and n2 we are writing xi1 times xi1 minus half multiplied by 2, and similarly for n2 we are writing as 2 times xi2 times xi2 minus half, you can also write n3 equal to xi3 2 times xi3 multiplied by xi3 minus half. We can write that, and we can also check it basically. So let's expand it. So we know that this will be equal to 2, xi3 is equal to 1 minus xi1 minus xi2, and here if we xi3 will be 1 minus xi1 minus xi2 and then minus half, so this becomes half. So this becomes half minus xi1 minus xi2. So we can check it, And how to check it? So let's see whether it will be 3, whether it will be 1 at node 3. So at node 3 we have xi1 xi2 both 0, so you put 0 here, so we get 0 here, 0 here, so this is left with 1 here, 0 here, 0 here, so you left with half. So 2 times 1 times half is 1, so n3, you see that at n3 at node 3 n3 equal to 1. Now let's check whether at node 1 it's 0 or not. So at node 1 we have coordinate system, coordinate 1 0, so you put 1 0 here, so 1 minus 1 minus 0 becomes 0, so automatically this becomes 0. Similarly you put here it is 0 1 is the coordinate, so you put 1 minus 0 minus 1, so this becomes 0, so hence 0. Similarly for 6 also you will get half half, so put here 1 minus half minus half, so 1 minus 1 equal to 0, so again becomes 0. At node 4 this is half 0, 0 half, this is half, 4 is 0 half is the coordinate system, so you put here 1 minus 0 minus half, so this becomes half, put here half minus 0 minus half, so this becomes 0. Similarly we can check it at node 5, we have coordinate here half 0, so put here 1 minus half minus 0, so this becomes half, then half minus half minus 0, half minus half becomes 0, so this becomes 0. So we see that n3 is 0 everywhere except at node 3 where the value is 1, so this is acceptable. Now we have to find out what is the n4. So n4, so in order to find out n4 we have to look at the two lines which will not include this one. So what we see here is one line is this one and one line is this one, so we can accordingly multiply it together. So this line is nothing but xi2 equal to 0, so we write xi2 here, okay. And what about this line? This line we know that this is xi3, this one is xi3, so this is becomes xi3, okay. So this is what we get, xi2 and xi3, okay. And then at 4 this is xi2 equal to 0, this is xi3 equal to 0, so we wrote like this one, and we know that the value will be n4 will be 1 at node 4 where the coordinates is both half and half. So basically at node 4 we have xi1 equal to 0 and xi2 equal to half, hence xi3 equal to 1 minus xi1 minus xi2, so 1 minus 0 minus half is half, so xi3 is also half. So at node 4 xi3 is half and xi2 is also half, so this becomes half times half, 1/4, this value becomes 1/4, so we have to multiply by 4 like this one, okay. Similarly what we get, n5, so what value we get for n5? So n5 again we have this multiplied by this one, and what is this one? This is xi3 and this is xi1, so xi3 equal to 0, xi1 equal to 0, so value will be 4 xi3 xi1 using the same logic here for n4. Similarly you will get n6 equal to, n6 here two lines, this line and that line, this line nothing but xi2 equal to 0 and this line is xi1 equal to 0, so this will be simply 4 xi1 and xi2, and 4 why? Because n6 will be 1 at node 6. At node 6 you have half and half. Put here half and half. 4 times half, you get 1. So n6 equal to 1, and it will be 0 at other nodes. So we got the 6 shape functions here. However, we have written here xi3, and we know that xi3 equal to 1 minus xi1 minus xi2, that we can replace. Xi3 can be replaced here with 1 minus xi1 minus xi2. Now if you want to find out the stiffness matrix, so we will extend what we learned earlier. So Ke vector, Ke matrix, that's the stiffness matrix. If you remember, we did in the last lecture video. So K is given by Bt dB d omega, and this is true for all kinds of elements. So that's why we derived this for general purpose element, that is valid for an element having any number of nodes. So this is what the stiffness function is, and the stiffness matrix is where B matrix, B is given by del S n, where n, where we write del S is nothing but del over del x, 0, 0, del over del y, and del over del y, and del over del x. So this is the operator matrix. And then n, and n, if you remember from last 2 lecture videos, so n becomes n1 0, n2 0, n3 0, n4 0, n5 0, and then n6 0. So since it has 6 nodes, hence it will have 6 times 2 equal to 12 columns, and here it will have 0, n1, 0, n2, 0, n3, 0, n4, 0, n5, and 0, n6. Okay, and this operator multiplied by this n matrix will determine B. However, note here is n here, in our case n is a function of xi1 and xi2, but here for the in the general derivation we assumed n1 n to be directly function of x and y. So we need to convert this from xy to xi1 xi2 system. So that's what we will do next. So what is the relation we have between xy system and xi1 xi2 system? So we have x equal to x3 plus x1 minus x3 xi1 plus x1 x2 minus x3 xi2, and similarly we have y equal to y3 plus y1 minus y3 xi1 plus y2 minus y3 times xi2. So, that means the relation we can also write dx equal to del x over del xi1 d xi plus del x over del xi2 d xi xi1 here, xi2 here. Similarly, dy is equal to dy over d xi1 d xi1 plus del y over del xi2 d xi2. Okay. So, this we can also write, combine them together, and we write like del dx dy is equal to del x over del xi1 del x over del xi2 del y over del xi1 del y over del xi2 and multiplied by d xi1 and d xi2, and we call this matrix as the Jacobian matrix J. So, this is J. And while studying the isoparametric elements, we also know that area in xy coordinate system is given by determinant of this Jacobian multiplied by area in the xi1 xi2 system. So, we will make use of this to build the stiffness matrix. That is, our first job is to how to express B matrix in terms of xi1 and xi2 coordinate system. So, similarly we can write del n1 del xi1 is equal to del n1 over x, then del x over del xi1 plus del n1 over del y and del y over del xi1. And similarly for all of them, so even we can write del n 2 for example over del xi1. In fact, we write like this, del ni equal to del ni over del x del xi1 plus del ni over del y and del y over del xi1. And similarly we can write del ni over del xi2 is equal to del ni over del x over del xi2 plus del ni over del y over del xi2. Okay. Or we can write it as del ni over del xi1 del ni over del xi2 is equal to, here there will be one matrix multiplied by del n I over del x and del ni over del y. So this we have done already while studying the isoparametric elements. I am repeating the same thing here. So what you get here is nothing but del x, so del x over del xi 1 and del y over del xi 1 del x over del xi 2 del y over del xi 2. So if you compare here, this we called the Jacobian matrix, where this is del x over del xi 1, del x over del xi 2. Here we have del x over del xi 1 and del x over del xi 2. So this is transpose of that. So this is J transpose basically. Yeah, so this is J transpose. We can write here like this is J transpose. So this we can write in terms of this one, means derivative with respect to xi 1 xi 2 can be written as J transpose multiplied by the derivative in terms of x y. In the original K matrix, B is in terms of original x y. So we have to find out this has to be equal to this inverse and this. Okay, so we write here, if we extend that, that will be del ni over del x, del ni del y will be equal to J inverse J transpose, but inverse of that, the J over minus T indicates inverse transpose, and then we have this one. So del ni over del xi 1 and del ni over del xi 2. So like this. Okay, so let's rewrite it here. So what we got so far is del n I over del x and del n I over del y equal to J inverse transpose and del n I del xi 1 del n I over del xi 2. Okay, so this can be extended further. Extended further means this is true for any I. So for I equal to 1, 2, 6. Actually, there are 6 shape functions. So basically, we can get each and every del n I over del x and del ni over del y. Remember, the original B matrix is has all of them. So by all of them, what I mean is it has del n 1 over del x, 0 del n2 over del x, 0 del n3 over del x, 0 del n4 over del x, 0 del n5 over del x, 0 del n6 over del x, 0. Okay, similarly it has here, so 0 del n1 over del y, 0 del n2 over del y, 0 del n3 over del y, 0 del n4 over del y, 0 del n5 over del y, 0 del n 6 over del y, and here del n 1 over del y, del n 1 over del x, del n 1 del n 2 over del y, del n 2 over del x, del n 3 over del y, del n 3 over del x, and so on, del n 4 over del y, del n 4 over del x, del n 5 over del y, del n 5 over del x, and so on, del n 6 over del y, del n 6 over del x. Okay, so this is same as what we got in last two video lectures, so you can revisit them. So what we get here is derivative of all the shape functions with respect to x and y, and since we know that n the shape functions are explicit functions of xi1 xi2, so we can get a derivative with xi1 xi2, and then here J inverse transpose J is also explicitly known because J is this matrix. Okay, so since we know that X is a function of xi1 xi2, so we can get this derivative, we can get this shape this Jacobian matrix. So Jacobian matrix is known, which will be a function of xi1 xi2. So this is function of xi1 xi2, this is also function of xi1 xi2. So we get n1 del ni over del x in terms of xi1 xi2, and those values we can put here to form the B matrix, and once we know the B matrix, we can get K E equal to what we get, BT dB and d omega. Now this omega is nothing but actually this is BT dB and dA xy. This is okay. So this is multiplied by the area in xy coordinate system. Yeah, so that we know that this will be nothing but dA becomes J. This becomes the determinant of J, and then d area in xi1 xi2 coordinate system. So we wrote like that. So we know that because of this transformation, we will get B in terms of xi1 xi2. D is constant, which does not have any xi1 xi2 there. B again is a function of xi1 xi2 because of this and these relations, and hence we will get here everything in terms of xi1 xi2, and once we have that, then we can do numerical integration to find out the stiffness matrix. Okay, so this is now in xi1 xi2 domain. Let's find out the J now. So the Jacobian matrix J is given by del x over del xi1, then del x over del xi2, del y over del xi1, and del y over del xi2. We can find out since we know x equal to x3 plus x1 minus x3 xi1 plus x2 minus x3 xi2. So del x over del xi1 is equal to x1 minus x3, and similarly we have y equal to y3 plus y1 minus y3 xi1 plus y2 minus y3 xi2, and hence del y over del xi1 is equal to y1 minus y3. Similarly, you can get del x over del xi2, which is here. So del x over del xi2 will get x2 minus x3. So hence we get x2 minus x3, and del y over del xi2 will be equal to y2 minus y3, like this one. Hence J matrix we have already derived, and we will put all those values x1 minus x3, and then x2 minus x3 here, then y1 minus y3 and y2 minus y3 here. Okay, so this is known now, we have derived already here, and this is nothing but what we did in other video lecture where we were discussing the isoparametric triangular element or quadrilateral element. Okay, now we can also find out these values. So for example, we had n1 and the value of n1 was xi1 and xi1 minus half, and here 2, like this. So we get del n1 over del xi1 is equal to, so we can expand it here. So what we get is 2 xi1 square minus xi1. So we get del n1 over del xi1 is equal to 4 xi1 minus 1. Okay. Here we have also with respect to xi2. So this we are determining for I equal to 1. So del n1 over del xi2 is equal to 0 because here there is no xi2. Okay. Similarly, we can find out del n2 is equal to 2 xi2 minus half is becomes 2 xi2 square minus xi2, and hence del n2 over del xi1 is equal to 0 because there is no xi1 there, and del n2 over del xi2 will be equal to 4 xi2 minus 1. Okay. Now n3 is equal to 2 xi3 minus half, and what we get here is 2 xi3 square minus xi3, or del n3 over del xi1 becomes equal to 4 xi3 times del xi3 over xi1 minus del xi3 over xi1, and we know that xi3, I can write here, where xi3 equal to 1 minus xi1 minus xi2, that makes is del xi3 over xi1 equal to minus 1, and so is xi3, del xi3 over del xi2 is equal to also minus 1. So what we get here is minus 4 xi3 plus 1. Okay, so here xi3 over del xi3 over del xi1 equal to minus 1, so we get minus because minus 4 xi3 plus 1 because del xi3 over del xi1 becomes is also minus 1. So this is what we get like this. Okay, so similarly del n3 and del xi2, del n3 over del xi2 will also be the same because the derivatives are same for xi3 with respect to xi1 and xi2 both. So we will write this is also equal to del n3 over del xi2. You can also check it. Similarly n4, so we know that n4 equal to 4 xi2 and xi3. So del n4 over del xi1 is equal to 4 xi2 del xi3 over del xi1, and this we know equal to minus 1, so hence this minus 4 xi2. Del n4 over del xi2 will be equal to 4 xi3 plus 4 xi2 del xi3 over del xi2, and which will be equal to 4 xi3, and this we know equal to minus 1, so and minus 4 xi2. Okay, where of course always wherever xi3 is, we have to write xi3 equal to 1 minus xi1 minus xi2. Okay, so n4 we have done. Now n5 equal to 4 xi3 xi1, so del n5 over del xi1 is equal to, okay, here simply 4 del xi3 over del xi1 plus 4 xi3 is equal to, this is minus 1, so because minus 4 xi1 plus 4 xi3 del n5 over del xi2 is equal to, here xi2. So xi1 is not function of xi2, so you get 4 del xi3 over del xi2 and xi1, and this is equal to -1, so -4 xi1. Lastly, n6 and n6 equal to 4 xi1 xi2, so del n6 over del xi1 is equal to 4 xi2, and del n6 over del xi2 equal to 4 xi1. Okay, so these are the derivatives of n with respect to xi1 and xi2, and remember, we can use this. Then once these are known, we can use this transformation to get del n over del x and del n over del y, and these values we can put here to get B matrix, and this B matrix you put here along with D to get the stiffness matrix. That is all for today. But let's write that at the end before we end this video lecture. So transformation, so del ni over del x del ni over del y is equal to J inverse transpose del ni over del xi1 del ni over del xi2. So this transformation we have to use to get this one, and this is included in B, and so we just write it here, Ke is equal to integral and bt dB. All of these together will be in xi1 in terms of xi1 and xi2. Then we have determinant of J and then dA in xi1 xi2 coordinate system, and integrated over the whole domain in xi1 xi2 domain. So write omega xi1 xi2. So this is how we get it. Okay, of course we use these in computers, so automatically taken care of actually. So doing manually may be very lengthy, and also the matrix, the Ke will be 12 by 12, so really it will require a lot of calculation. So this is better for computers only. Okay, that's all.